Hello there, and welcome. Get comfortable, take a deep breath, and let yourself settle in as we embark on a gentle journey through the cosmos tonight. This is a space where curiosity meets calm, where we can let our minds wander through the infinite while our bodies rest and relax. Tonight, we're going to explore one of the most profound questions humanity has ever asked. What lies beyond the edge of everything we can see? Let these thoughts carry you softly, like drifting on a quiet sea under the stars. When you look up at the night sky, you're seeing light that has travelled for years, sometimes millions or even billions of years, to reach your eyes. Every star, every distant galaxy, every cosmic wonder visible to us exists within what astronomers call the observable universe. But here's the thing that keeps scientists awake at night, though tonight it might just help you drift peacefully to sleep. The observable universe has an edge. Not a physical wall or barrier, but a boundary beyond which light simply hasn't had enough time to reach us since the beginning of the universe itself. So what's out there beyond that boundary? What exists in the vast cosmic regions that remain forever hidden from our view? The answers might surprise you, challenge your intuition, and perhaps leave you with even more questions than when we started. But that's exactly what makes this journey so fascinating, and so perfectly suited for letting your mind gently wander as your body finds its rest. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable, dim the lights, close your eyes if you'd like, let the city noise fade away, and let's begin. Let's begin by understanding what we actually mean when we talk about the observable universe. Imagine you're standing in the middle of an enormous, fog-filled room. You have a flashlight, but the fog is so thick that you can only see a certain distance, in any direction. Beyond that distance, the fog obscures everything. The observable universe is somewhat similar, except instead of fog, we're limited by the speed of light and the age of the universe. The observable universe is approximately 93 billion light-years in diameter. Now, you might be thinking, wait, if the universe is only about 13.8 billion years old, shouldn't we only be able to see 13.8 billion light-years in each direction? That's a perfectly reasonable question, and it reveals something fascinating about the nature of space itself. The universe has been expanding since the Big Bang, and not only expanding, but the space between distant galaxies has been stretching. This means that light from distant objects has been travelling toward us for billions of years, but during that time the space it was travelling through was also expanding. An object that emitted light 13.8 billion years ago is now much farther away than 13.8 billion light-years because of this expansion. Scientists currently think that object is now about 46.5 billion light-years away, which is why our observable universe has a radius of roughly that distance. Think of it this way. Imagine you're trying to walk toward a destination, but with every step you take forward, the ground itself stretches, moving your destination a bit farther away. You're still making progress, but the finish line keeps receding. Light travelling through expanding space faces a similar challenge. This creates what cosmologists call our cosmic horizon, or light horizon. It's the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon, there could be countless galaxies, stars, and cosmic structures, but their light simply hasn't had enough time to reach us yet. The universe might be infinitely large, but we're confined to observing only this finite sphere around us. But here's where things get really interesting. This horizon isn't static. Every second that passes, light from slightly more distant regions has time to reach us. Our observable universe is actually growing, although very slowly on cosmic timescales. In principle, we could eventually see more and more of the cosmos as time goes on. However, there's a complication. one that fundamentally limits what we'll ever be able to see. In the late 1990s, astronomers made a discovery that shocked the scientific community and eventually earned a Nobel Prize. They found that the universe's expansion isn't just continuing, it's accelerating. Distant galaxies aren't just moving away from us, they're moving away faster and faster over time. This acceleration is attributed to something we call dark energy, a mysterious force that appears to be pushing space itself apart. Scientists currently think dark energy makes up about 68% of all the energy in the universe, yet we don't really understand what it is. We just know it's there because we can observe its effects on cosmic expansion. What does this mean for our observable universe? It creates a cosmic catch-22. While light from distant regions is travelling toward us, those regions are being carried away by the expansion of space. And because this expansion is accelerating, there are galaxies out there that are receding from us faster than their light can reach us. We'll never see these galaxies no matter how long we wait. In fact, there are galaxies we can see right now that we'll eventually lose sight of as they're carried beyond our cosmic horizon by accelerating expansion. Think of it as being on a treadmill that keeps speeding up. You're running forward as fast as you can, but if the treadmill accelerates faster than you can run, you'll be carried backward no matter how hard you try. Light from extremely distant regions faces the same problem when racing against accelerating cosmic expansion. This means our observable universe has a sort of ultimate horizon, beyond which we can never receive information, no matter how long we wait. This horizon is roughly at a distance where space is expanding faster than the speed of light. And yes, space itself can expand faster than light. That doesn't violate relativity, because no object is actually moving through space faster than light. Instead, the space between objects is growing. So we've established what the observable universe is and why it has limits. But what about the universe beyond those limits? What's actually out there in the regions we can't see? Beyond the edge, the unobservable universe. Here's where we need to be careful about how we think about this question. When we ask what exists beyond the edge of the observable universe, we're not asking about what's beyond the edge of the universe itself. Evidence suggests the universe doesn't have an edge in that sense. Instead, we're asking about what exists beyond the boundary of what we can observe. The simplest and most likely answer, based on our current understanding of cosmology, is this: more of the same. The observable universe appears remarkably uniform on large scales. When we look in any direction, we see roughly the same types of structures: galaxies, galaxy clusters, vast cosmic voids, and the same physical laws governing everything. This uniformity is called the cosmological principle, which states that on sufficiently large scales, the universe looks basically the same everywhere. It's homogeneous, meaning it has the same composition throughout, and isotropic, meaning it looks the same in all directions. If this principle holds true beyond our observable limits, then the unobservable universe should contain more galaxies, more stars, more planets, all following the same physical laws we observe here. There's no reason to think that just beyond our cosmic horizon the universe suddenly becomes radically different. But how far does this continue? Does the unobservable universe go on forever, or does it have a finite size? This is one of the biggest open questions in cosmology, and the honest answer is, we don't know for certain. However, scientists have different models that make predictions, and we can explore the possibilities. The geometry of space, flat, open, or closed? To understand whether the universe is finite or infinite, we need to talk about the geometry of space itself. This might sound abstract, but bear with me. It's actually quite fascinating. In our everyday experience, space seems flat. If you draw a triangle on a piece of paper, the angles add up to 180 degrees. Parallel lines never meet. But Einstein's general relativity taught us that space itself can be curved by matter and energy. There are three basic possibilities for the geometry of the universe on the largest scales. First, the universe could be flat. In a flat universe, the rules of geometry we learned in school apply on cosmic scales. Parallel lines remain parallel forever, and the universe would likely be infinite in size. If you could somehow travel in a straight line forever, you'd never return to your starting point. You'd just keep going through endless space. Second, the universe could be positively curved, like the surface of a sphere. In this closed universe, if you travelled far enough in one direction, you'd eventually return to where you started. Like an ant walking around a balloon, parallel lines would eventually converge. This type of universe would be finite in size but wouldn't have an edge or boundary, just as the surface of a sphere has no edge. Third, the universe could be negatively curved, like a saddle shape. This open universe would be infinite and have what mathematicians call hyperbolic geometry, where parallel lines diverge from each other over distance. So which is it? Scientists have measured the geometry of our universe with increasing precision, particularly by studying the cosmic microwave background radiation, the afterglow of the Big Bang. The measurements consistently show that to the best of our ability to measure, the universe appears to be flat or extremely close to flat. Current data suggests that if the universe has any curvature, it's so slight that it would have to extend to at least hundreds of times the size of our observable universe before we'd notice the curvature. A flat universe, according to most models, would be infinite in extent. This would mean the unobservable universe doesn't just extend a bit beyond what we can see. It goes on literally forever in all directions. An infinite universe containing infinite matter and energy, infinite galaxies, infinite stars, infinite planets. Can you wrap your mind around that? The implications of infinity. If the universe is truly infinite, the implications are staggering and, frankly, quite strange. In an infinite universe with matter distributed relatively uniformly, every possible configuration of particles would not only exist somewhere, but would exist infinitely many times. This is a consequence of probability in an infinite space. Even if an event is extremely unlikely, given infinite trials, it will occur infinitely often. What does this mean practically? It means there would be other regions of space, unfathomably far away, that are identical to the region around us. There would be other planets exactly like Earth, with people exactly like you, reading a script exactly like this one. In fact, there would be infinitely many such copies. There would also be planets almost identical to Earth, with just tiny differences, perhaps where you chose a different career, or where World War II had a different outcome, or where dinosaurs never went extinct. This isn't science fiction or wild speculation. It's a straightforward mathematical consequence of an infinite universe with finite possible arrangements of matter within any given volume. If you have infinite volumes of space, even incredibly rare configurations must repeat. Scientists have calculated that if the universe is infinite and uniform, you'd only need to travel about 10 to the power of 1029 meters away. That's a 1 followed by about 10 trillion zeros to find a region of space identical to our observable universe. That distance is so absurdly large it makes our observable universe look like a grain of sand on a cosmic beach. But in an infinite universe, such a region wouldn't just exist, it would exist infinitely many times. Does this bother you? It should, at least a little. It certainly bothers many physicists who find the idea philosophically troubling. But nature isn't obligated to conform to what we find intuitive or comfortable. Of course, we need to remember that even though this follows logically from an infinite, uniform universe, we don't know with absolute certainty that the universe is infinite. Measurements show it's at least flat within our observable region, but it could have slight curvature that only becomes apparent over much larger distances. And there are other possibilities we haven't discussed yet. The multiverse, multiple universes beyond ours. So far, we've been assuming that beyond our observable universe, there's simply more universe, more space filled with matter and energy, following the same laws of physics. But some theoretical frameworks suggest something even more radical. There might be other universes entirely, completely separate from ours, existing in some higher dimensional space, or emerging from different quantum outcomes. The concept of a multiverse comes in several different flavors, each based on different areas of theoretical physics. Let's explore a few. First, there's the quilted multiverse, which is actually just the infinite universe we discussed before. In this picture, if space goes on forever, then by probability alone, there are other universes out there that are causally disconnected from ours, so far away that we can never interact with them or observe them. They're not separate universes in a strict sense, just incredibly distant regions of the same space. Then there's the inflationary multiverse, which emerges from cosmic inflation theory. Scientists currently think the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. This inflation theory helps explain several observed features of our universe, like why it's so uniform on large scales. But here's the intriguing part. Some versions of inflation theory suggest that while inflation ended in our region of space, allowing our observable universe to form, it continues eternally in other regions. These eternally inflating regions might occasionally spawn new bubble universes, each with its own Big Bang and potentially its own physical laws. Our entire observable universe would be just one bubble in an endless, inflating cosmos full of other bubbles. In this scenario, beyond the edge of our observable universe, you'd eventually reach the edge of our universe bubble. And beyond that, other universe bubbles, some potentially with different fundamental constants, different numbers of dimensions, or even different types of particles and forces. These bubble universes would be truly separate, not just distant regions of the same space, but distinct spacetimes that emerge from different points in the eternal inflation process. There's also the quantum multiverse, arising from certain interpretations of quantum mechanics. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. If this interpretation is correct, there would be countless parallel universes, one for every possible quantum outcome that's ever occurred. Somewhere in this multiverse, there's a universe where the asteroid missed Earth and dinosaurs still rule the planet. Somewhere else, you chose a different breakfast this morning. The implications are dizzying. Finally, string theory and M theory, which attempt to unify quantum mechanics and gravity, suggest the possibility of extra dimensions beyond the three spatial dimensions we experience. These theories raise the possibility of a brain multiverse, where our universe is a three-dimensional membrane floating in a higher dimensional space. And other universe brains might exist nearby in these extra dimensions. If two brains collided, it might even trigger a Big Bang event, creating a new universe. Now, I need to be clear about something important. These multiverse concepts, while based on legitimate physics and mathematics, are highly speculative. We currently have no direct evidence that any of these other universes exist. They emerge as possibilities from extending certain well-tested theories, but that doesn't mean they're real. Many physicists are skeptical of multiverse theories precisely because they might be impossible to test scientifically. If we can never observe these other universes, even in principle, are they really science or more like metaphysics? This is an ongoing debate in the physics community. Some scientists argue that even if we can't directly observe other universes, we might find indirect evidence in the form of patterns in our own universe that would be highly improbable without a multiverse. Others maintain that untestable theories aren't science at all, regardless of how mathematically elegant they might be. But these ideas give us a sense of just how strange the answer to our question might be. What exists beyond the edge of the observable universe could be more universe, very much like our own. Or it could be other universes, bubbles in an eternally inflating cosmos, or quantum branches where every possible history plays out, or higher dimensional spaces beyond our comprehension, or perhaps something we haven't even imagined yet, the structure of the universe. What do we actually observe? Before we go too far down the rabbit hole of speculation, let's ground ourselves in what we actually observe and what that tells us about the likely structure of the unobservable universe. When astronomers map the observable universe, they find a remarkable structure called the cosmic web. Galaxies aren't randomly scattered through space. Instead, they're organized into a vast interconnected network of filaments and sheets, separated by enormous voids where few galaxies exist. Imagine a foam or a sponge. The solid parts of the sponge represent filaments of galaxies, and the empty spaces represent cosmic voids. This is what the large-scale structure of the universe looks like. Galaxy clusters sit at the intersections of these filaments, like cities at highway junctions, while the voids between them can be hundreds of millions of light-years across, with very few galaxies inside. This structure emerged from tiny quantum fluctuations in the very early universe that got stretched to cosmic scales during inflation. Over billions of years, gravity amplified these initial density variations, pulling matter together into the web-like structure we observe today. The crucial point is this: when we look at the observable universe as a whole, it appears statistically uniform. Yes, there are local variations, galaxies, clusters, voids, but on the very largest scales, the density of matter is roughly the same in all directions. If you could somehow zoom out and view the entire observable universe, it would look like a relatively smooth, uniform distribution of matter. This uniformity strongly suggests that the unobservable universe is probably similar. There's no reason to think that just beyond our cosmic horizon, the universe suddenly becomes fundamentally different. The same physical processes that created structure in our region would operate in distant regions. The same gravitational laws, the same quantum fluctuations, the same cosmic evolution. Of course, there could be differences we can't account for. Perhaps in some distant region, conditions in the early universe were slightly different, leading to a region with more or fewer galaxies than average. Or perhaps, and this is where we enter more speculative territory, different regions underwent inflation at different times or in different ways, leading to genuine variations in physical properties. But based on what we can observe and measure, the most likely scenario is that the unobservable universe is, well, pretty much like the observable one. More cosmic web, more galaxies, more stars, more planets, the same physics, the same fundamental forces, the same types of particles. Is that disappointing? Perhaps it lacks the exotic strangeness of bubble universes or quantum branches, but there's something profound in its own way about a universe that simply continues, possibly forever, full of wonders we'll never see, stories we'll never know, and civilizations we'll never meet. The question of life beyond our cosmic horizon. This brings us to an interesting question. If the unobservable universe contains countless galaxies and stars, how many of those stars have planets? And how many of those planets host life? In our observable universe alone, we now know that planets are common. Nearly every star has at least one planet orbiting it. That means our observable universe contains something like 200 billion trillion stars. That's 2x10^23, and potentially even more planets. Among all those planets, Earth certainly can't be the only one hosting life. Scientists currently think life requires a few key ingredients: liquid water, organic chemistry, and an energy source. Many planets and moons in our own solar system might meet these criteria in subsurface oceans or ancient seas. Europa, Enceladus, and Mars are prime candidates for finding evidence of life, whether extinct or still active. Extrapolating outward, the observable universe likely contains countless worlds with life. Some might host simple microbes, others might have complex ecosystems. And somewhere out there, perhaps many times over, intelligent civilizations might have arisen, built technologies, asked their own questions about what lies beyond their cosmic horizon. Now extend this reasoning to the unobservable universe. If it's infinite, or even just vastly larger than what we can see, then the number of life-bearing worlds becomes staggering, potentially infinite. Every possible evolutionary path would be taken somewhere. Every possible form of life, every possible civilization, every possible destiny for an intelligent species. There would be civilizations far more advanced than ours, perhaps millions or billions of years ahead in their development. They might have technologies that seem like magic to us, might have solved problems we consider impossible, might have spread across their own galaxies and beyond. And there would also be countless civilizations in their infancy, just beginning to ask questions about their universe, just starting to develop technology, just awakening to the cosmic perspective. None of them could ever communicate with us. The distances involved, combined with the expansion of space, make communication impossible. We're forever isolated, confined to our own cosmic neighborhood, unable to share knowledge with, or even confirm the existence of our cosmic cousins. Does this make you feel lonely? Or perhaps comforted by the thought that we're probably not alone, even if we're forever separated? The edge of knowledge? What can we ever hope to know? One of the most philosophically challenging aspects of asking what exists beyond the observable universe is that we're asking a question that might be fundamentally unanswerable. We're not limited by current technology or our present understanding. We're limited by the laws of physics themselves. No matter how advanced our telescopes become, no matter how sophisticated our theories, we can never receive information from beyond our cosmic horizon. The light from those regions simply can't reach us, and no signal travels faster than light. In some sense, asking what exists beyond the observable universe is like asking what happened before the Big Bang. It might be a question without meaning, or at least without any possible empirical answer. This raises deep questions about the nature of scientific knowledge. Science works by observing the universe, forming hypotheses, and testing them against observations. But what do we do with questions that can't be tested, even in principle? Are they still scientific questions? Or do they cross into philosophy or metaphysics? Some scientists argue that we should focus only on what we can observe and measure. Questions about the unobservable universe, they say, are interesting for speculation, but ultimately not productive for science. We should concern ourselves with understanding the universe we can see. Others counter that theoretical reasoning about the unobservable universe is legitimate if it's grounded in well-tested physics. If our theories about the observable universe naturally extend to make predictions about the unobservable universe, those predictions deserve serious consideration, even if we can't verify them directly. There's also a middle ground. Perhaps we can't directly observe what's beyond our cosmic horizon, but we might find indirect evidence. For example, if we detected subtle patterns in the cosmic microwave background radiation that could only be explained by collisions with other universe bubbles during inflation, that would provide indirect evidence for the multiverse, or if we found variations in fundamental constants across our observable universe, it might suggest that different regions had different properties, hinting at what lies beyond. The challenge is designing tests that are both rigorous and feasible. It's one thing to propose that evidence might exist, it's another to actually find and verify it. The evolution of our understanding. How views have changed. It's worth reflecting on how our understanding of this question has evolved over time. For most of human history, we didn't even realize there was anything beyond our immediate cosmic neighborhood. Ancient civilizations believed Earth was the center of the universe, with everything revolving around us. The discovery that Earth orbits the Sun was revolutionary. Then we learned that the Sun is just one star among billions in our galaxy. Then we discovered that our galaxy is just one among billions of galaxies. Each revelation pushed the boundaries of our cosmic perspective outward. Even in the early 20th century, many astronomers believed the Milky Way was the entire universe. The fuzzy nebulae visible in telescopes were thought to be gas clouds within our galaxy. It wasn't until the 1920s that Edwin Hubble proved these nebulae were actually distant galaxies, millions of light years away. Our universe suddenly became vastly larger. Then Hubble made another groundbreaking discovery. The universe is expanding. This wasn't just an expansion of matter into pre-existing space. Space itself was growing. This observation led directly to the Big Bang theory and our modern understanding of cosmic evolution. Throughout the 20th century, our picture of the universe continued to transform. We discovered the cosmic microwave background radiation, providing direct evidence for the Big Bang. We mapped the large-scale structure of the universe. We measured its age, composition, and rate of expansion with increasing precision. We discovered dark matter and dark energy, revealing that the familiar matter we're made of constitutes only about 5% of the universe's total energy content. And we realized that the observable universe, as vast as it is, might be just a tiny fraction of what exists. This realization came from both observational evidence, like the flatness of space, and theoretical developments, like inflation theory and the multiverse concept it spawned. What will the next century bring? Will we find evidence for other universes? Will we discover new physics that revolutionizes our understanding of what's possible? Or will we conclude that some questions, like what exists beyond our cosmic horizon, are simply beyond our ability to answer? The philosophical implications, our place in an incomprehensible cosmos. Contemplating what exists beyond the edge of the observable universe forces us to confront some profound philosophical questions about our place in the cosmos. If the universe is infinite, or if there's a multiverse with countless other universes, what does that mean for the significance of anything that happens here? Does our existence matter in a cosmos so vast that everything that can happen does happen, infinitely, many times? Some find this perspective nihilistic. If there are infinite copies of you making every possible choice, does any particular choice matter? If our entire observable universe is just one bubble in an infinite foam, does anything we do have cosmic significance? But you could look at it differently. Perhaps what matters isn't cosmic significance, but local significance. Your actions matter to you, to the people around you, to your community and world. The fact that there might be other versions of you elsewhere doesn't diminish your experiences, your relationships, or your impact on your corner of the universe. There's also something oddly comforting about the possibility that we're not alone, even if we're forever separated from others. If the universe or multiverse is vast enough, then life, intelligence, and consciousness probably emerge in countless locations. We might be cosmically isolated, but we're not unique or special in the sense of being the only ones asking these questions. The observable universe alone is so large that we'll never fully explore it. Humanity could last for billions of years and never run out of new places to discover within our cosmic horizon. The stars we see in the night sky represent just a tiny fraction of the stars in our galaxy, which is itself just one among trillions. We have an entire universe to explore right here, even before worrying about what lies beyond. Yet we can't help but wonder. It's part of human nature to push at boundaries, to ask what lies beyond the horizon. Ancient explorers wondered what lay beyond the seas. We wondered what was on the other side of the moon. And now we wonder what exists beyond the cosmic horizon. The specific frontiers change, but the drive to explore, to know, to understand remains constant. What physics tells us, constraints on the unknown. While we can't directly observe what exists beyond the observable universe, physics does place some constraints on what's possible out there. For instance, we understand the laws of thermodynamics pretty well, and these laws should apply everywhere, even beyond our cosmic horizon. The second law of thermodynamics tells us that entropy, disorder, tends to increase over time. This means that in the distant future, even regions we can't see now will likely evolve toward a state of maximum entropy, what physicists call heat death. Eventually, all the stars will burn out, all the black holes will evaporate through Hawking radiation, and the universe will become a thin, cold soup of particles spreading ever farther apart. This fate seems to await not just our observable universe, but any region of space, governed by the same physical laws. Unless there's some new physics we don't understand yet, the long-term future of the universe, both observable and unobservable, is one of increasing cold, darkness, and emptiness. We also understand how structure forms in the universe through the gravitational collapse of matter following the initial density fluctuations from the early universe. This process should work the same way everywhere. So while we can't see what specific structures exist beyond our cosmic horizon, we can be fairly confident they formed through the same processes we observe here. The fundamental constants of nature, things like the strength of gravity, the charge of an electron, and the speed of light, appear to be the same throughout our observable universe. If the universe is simply larger than what we can see, these constants probably remain the same in the unobservable regions as well. However, some multiverse theories suggest different universe bubbles could have different values for these constants. In most such universes, the constants might not allow for the formation of atoms, stars, or any structure at all. We exist in a universe bubble with constants that allow for complexity and life, perhaps selected from among many bubbles by anthropic reasoning. We observe this universe because we couldn't exist in most of the others. There's also the question of causality. Physics tells us that causes must precede effects, and no influence can travel faster than light. This means that regions beyond our observable universe are causally disconnected from us. Nothing happening there can affect us, and nothing we do can affect them. In a real sense, those regions are in their own separate universes, even if they're part of the same continuous space. The role of dark energy shaping the future of observation. We discussed earlier how dark energy is causing the expansion of the universe to accelerate, but it's worth exploring in more detail how this affects what we'll be able to see in the future. Dark energy, whatever it is, appears to be a property of space itself. As space expands, more dark energy comes into existence, which drives even faster expansion, creating more space and more dark energy in a runaway process. Current observations suggest dark energy's strength is roughly constant per unit volume of space, which leads to exponential expansion on cosmic timescales. What does this mean for the observable universe billions of years from now? As the universe continues to expand and accelerate, distant galaxies will recede from us faster and faster. Eventually, galaxies beyond our local group will recede so rapidly that their light becomes too redshifted, stretched by expansion to detect. They'll fade from view one by one, disappearing beyond the cosmic horizon. In the far future, hypothetical astronomers living in our galaxy or its merged remnants would observe a very different universe than we do. They might see only a few nearby galaxies and a largely empty cosmos beyond. The cosmic microwave background radiation would be stretched to such long wavelengths it would be undetectable. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, all would be much harder to find. Those future astronomers might conclude they live in a static, isolated island universe, much like astronomers before Hubble thought the Milky Way was the entire cosmos. They'd be wrong, but they'd have no easy way to know they were wrong because the evidence would have literally disappeared beyond their horizon. This has an unsettling implication. What evidence might we be missing today? What features of the universe might have already receded beyond our horizon, leaving us with an incomplete picture? Could there be crucial clues about the nature of reality that were observable in the early universe, but are no longer accessible to us? We can't know what we can't see, but recognizing this limitation is important for staying humble about how much we actually understand. Alternative theories? What if we're wrong about everything? So far, we've been working within the framework of the standard model of cosmology, which includes the Big Bang, cosmic inflation, dark matter, and dark energy. This model fits the observational data remarkably well, but science progresses by questioning assumptions, and it's worth considering alternative theories, even if they're less mainstream. Some physicists have proposed that what we interpret as cosmic expansion could actually be something else. Perhaps time itself is changing, or the fundamental constants are evolving in ways that mimic expansion. These theories remain on the fringe because they generally don't explain the data as well as the standard model, but they remind us that our current understanding isn't necessarily the final word. There are also theories about cyclic universes, where instead of a single Big Bang, the universe goes through endless cycles of expansion and contraction. In these models, our Big Bang might have been preceded by a previous universe that collapsed down to a point before bouncing back into expansion. What exists beyond our observable universe in this view might include regions in different phases of the cycle, or even remnants from previous cosmic epochs. Another alternative approach comes from digital physics, which proposes that the universe might be computational in nature, essentially a simulation running on some vast substrate. If this were true, questions about what exists beyond the observable universe might be questions about the computational resources and structure of the simulation itself. Do unrendered regions exist in the same way that rendered regions do? Where are the boundaries of the simulation? Are there other simulations running in parallel? To be clear, these alternative theories remain speculative and lack the evidentiary support of the standard cosmological model. But they illustrate that what exists beyond the observable universe depends heavily on which theoretical framework you're working within. If our current model is missing something important, the answer to our central question could be very different from what we currently think. The limits of human understanding. Can we comprehend the answer? There's another challenge we face in answering what exists beyond the observable universe. Even if we somehow discovered the truth, would we be capable of understanding it? Human brains evolved to navigate a world of medium-sized objects, moving at everyday speeds. We're good at understanding things we can see, touch, and manipulate. We can extend our understanding through mathematics and technology, but there may be fundamental limits to what kinds of concepts we can truly comprehend. We can write down the equations of quantum mechanics and use them to make incredibly accurate predictions. But even the physicists who work with these equations daily will admit they don't really understand quantum mechanics in an intuitive sense. It doesn't match our evolved intuitions about how reality works. We've learned to calculate with it, but grasping what it means remains elusive. If quantum mechanics at the microscopic scale challenges our intuitions, how much more difficult might it be to truly understand the structure of the cosmos at the largest scales? Concepts like infinite space, eternal inflation, quantum branching, or higher dimensions might be fundamentally beyond our ability to visualize or intuitively grasp, even if we can work with them mathematically. There's also the possibility that the universe operates according to principles we haven't discovered yet. New physics, new mathematics, new frameworks for understanding reality. If such principles exist, they might be necessary for truly understanding what lies beyond our cosmic horizon, but we might not discover them for centuries or even millennia. This doesn't mean we should give up on trying to understand. Even if complete understanding is beyond us, partial understanding is valuable. We might not be able to visualize infinity, but we can work with it mathematically and draw logical conclusions about what it implies. We might not intuitively grasp higher dimensions, but we can explore their mathematical properties and see what they predict about observable phenomena. The history of science is full of examples of humans expanding their conceptual horizons to understand things that once seemed incomprehensible. We can understand that Earth is a sphere, even though it looks flat from our perspective. We can understand that we're moving through space at tremendous speeds, even though we feel stationary. We can understand that time passes at different rates depending on gravity and velocity, even though that contradicts our intuitions. Perhaps, given enough time and effort, we can expand our understanding enough to truly grasp what exists beyond the observable universe. Or perhaps this question will always remain at the edge of comprehensibility, tantalizing, but forever just out of reach. The search for evidence. What are scientists looking for? Even though we can't directly observe what's beyond our cosmic horizon, scientists continue to search for indirect evidence that might constrain the possibilities. One approach involves studying the cosmic microwave background radiation in ever greater detail. This radiation, released about 380,000 years after the Big Bang, when the universe first became transparent to light, carries information about the early universe. Tiny temperature fluctuations in this radiation reflect density variations that eventually grew into galaxies and galaxy clusters. Scientists have mapped these fluctuations with incredible precision using satellites like COBE, WMAP, and Planck. They're looking for patterns that might reveal something about the larger structure of the universe beyond what we can see. For example, if our observable universe were just one bubble among many, and if our bubble had collided with another during the inflationary epoch, such a collision might leave a distinctive mark in the cosmic microwave background, perhaps a circular pattern of slightly warmer or cooler temperatures in one region of the sky. So far, searches for such collision signatures have come up empty, but that doesn't rule out the multiverse. It just means that if other universe bubbles exist, we haven't collided with any recently enough to leave a detectable mark. Scientists continue to analyze the data, looking for subtle anomalies that might point to physics beyond the standard model. Another avenue of research involves studying the fundamental constants of nature and asking whether they could have different values. If we found that these constants are fine-tuned in ways that seem implausible by chance, it might support the idea of a multiverse where different regions have different constants, and we happen to exist in one that allows for complex structures and life. This is called the anthropic principle, the observation that any universe capable of being observed must have properties compatible with the existence of observers. If there's only one universe, and its constants were chosen at random, the fact that they happen to allow for life seems remarkably lucky. But if there are countless universes with different constants, it becomes less surprising that at least some of them would be life-permitting, and we naturally find ourselves in one of those. However, anthropic reasoning remains controversial. Some physicists find it compelling, while others argue it's unfalsifiable and therefore unscientific. The debate continues. Scientists are also studying the large-scale structure of the universe, looking for patterns that might extend beyond what we can observe. If we found evidence that our observable universe is part of some larger repeating structure, it might tell us something about what exists beyond our horizon. So far, the universe appears maximally random on large scales, with no evidence of repeating patterns, but this remains an active area of research. Gravitational wave astronomy, which has opened a new window on the universe in recent years, might eventually provide clues as well. These ripples in space-time could potentially carry information about cosmic events that occurred very far away or very early in cosmic history, perhaps even before the cosmic microwave background was released. As gravitational wave detectors become more sensitive, they might reveal new information about the universe's structure and history. There's also ongoing work in particle physics that might shed light on our questions. If scientists at facilities like the Large Hadron Collider discover new particles or forces, these findings might inform theories about the early universe, inflation, and the possible existence of other universe bubbles or higher dimensions. Every new discovery in fundamental physics has the potential to reshape our understanding of cosmology. The far future. Will our descendants know more? Assuming humanity or our descendants survive for millions or billions of years, will they have better answers to our question than we do? In some ways, yes. Future civilizations will have access to more sophisticated technology, more computational power, and potentially new theoretical frameworks we haven't developed yet. They might find ingenious ways to extract information from the cosmos that we can't currently imagine. But in other ways, the situation might actually be worse. As we discussed, the accelerating expansion of the universe means that distant galaxies are gradually disappearing beyond our cosmic horizon. Evidence that's available to us today, like the observation of distant galaxies and the cosmic microwave background, might become much harder or impossible to detect billions of years from now. There's a particular irony here. We happen to be living at a time when the universe is old enough that we can observe a great deal of its history and structure, but not so old that most of the evidence has disappeared. We're in what you might call a golden age of cosmological observation. Our distant descendants might envy the clear view of the cosmos we have today. Of course, this assumes the universe continues to evolve according to our current understanding. If there are surprises in store, unexpected phase transitions, changes in dark energy, or new phenomena we haven't predicted, the future might be very different from what we expect. Future civilizations might also develop technology that seems like science fiction to us. Could there be ways to probe beyond the cosmic horizon using methods we haven't thought of? Could advanced civilizations somehow manipulate space-time itself, creating shortcuts or windows through which to observe distant regions? Could quantum effects or exotic physics we don't yet understand provide loopholes in what we think are fundamental limitations? We can't rule out these possibilities, but we also can't count on them. The universe might be more constrained than we'd like, with hard limits on what's possible. Or it might be weirder and more malleable than we imagine. We simply don't know. What we can say is that every generation of scientists has expanded our understanding beyond what their predecessors thought possible. From Earth-centered cosmology to the heliocentric model, to galaxies beyond the Milky Way, to the expanding universe, to dark matter and dark energy, each generation push back the boundaries of ignorance. There's no reason to think this process has reached its end with us. The practical side, does this question actually matter? You might reasonably ask, does it actually matter what exists beyond the observable universe? If we can never observe it, never reach it, never interact with it in any way, is this question anything more than idle philosophical speculation? There are several answers to this question, depending on your perspective. From a purely practical standpoint, focused on immediate human concerns, no, it doesn't matter much. Whether the unobservable universe contains more galaxies, other universe bubbles, or quantum branches probably doesn't affect your daily life, the economy, medical treatments, or technology development. But from the perspective of fundamental understanding, it matters a great deal. Humans have always sought to understand our place in the cosmos. These questions have driven scientific progress throughout history. The ancient Greeks wondered about the nature of matter and developed atomic theory. Renaissance astronomers wondered about Earth's place in the solar system and revolutionized our worldview. Modern cosmologists wonder about the nature and extent of the universe, and this inquiry has led to breakthrough discoveries in physics, mathematics, and philosophy. Many of the most important scientific discoveries weren't motivated by practical concerns, but by pure curiosity about how nature works. Einstein developed relativity not to build GPS systems, but to understand the fundamental nature of space, time, and gravity. Quantum mechanics emerged from trying to understand atomic spectra, not from trying to build computers or smartphones. Yet both theories have led to transformative technologies. Similarly, trying to understand what exists beyond the observable universe might lead to unexpected discoveries along the way. The technologies we develop to probe the cosmos, the theoretical frameworks we create to explain our observations, and the mathematical tools we invent to handle these problems often find applications we never anticipated. There's also immense cultural and philosophical value in understanding our cosmic context. Every civilization has developed cosmologies, stories about the nature and origin of the universe. Our scientific cosmology is humanity's most sophisticated attempt yet to answer these ancient questions. Understanding that the universe might be vastly larger than what we can see, or that other universes might exist, or that reality might be far stranger than we imagined. These ideas transform how we think about ourselves and our place in existence. And perhaps most importantly, asking these questions is simply part of what makes us human. We're curious creatures. We want to know. The desire to understand, to push at the boundaries of knowledge, to ask, what's beyond the horizon? This drive has been with us since our ancestors first looked up at the stars and wondered. Indulging that curiosity, following that impulse to explore and understand, is valuable in itself, regardless of practical applications. What we've learned so far. Summarizing our journey. Let's take a moment to recap what we've explored on this journey beyond the edge of the observable universe. We started by understanding what the observable universe actually is, a sphere roughly 93 billion light-years in diameter, centered on us, representing all the regions of space from which light has had time to reach us since the Big Bang. This observable universe has an edge not because the universe ends there, but because we're limited by the speed of light and the age of the universe. We learned that the universe's expansion is accelerating due to dark energy, creating a fundamental limit on what we can ever observe. Some regions are receding so rapidly that their light will never reach us, no matter how long we wait. We explored the most straightforward answer to what exists beyond our cosmic horizon, probably more of the same. The observable universe appears uniform on large scales, and there's no reason to think that pattern doesn't continue beyond what we can see. If the universe is flat, as measurements suggest, it's likely infinite, containing infinite galaxies, infinite stars, and infinite planets. We grappled with the strange implications of infinity, including the unsettling possibility that every possible arrangement of matter exists somewhere, including perfect copies of our observable universe and everyone in it. We ventured into more speculative territory, exploring various multiverse concepts: the quilted multiverse of infinite space, the inflationary multiverse of eternal inflation spawning bubble universes, the quantum multiverse of many worlds, and the brain multiverse of higher dimensions. Each offers a different perspective on what might exist beyond our cosmic horizon, though none are proven. We considered what physics tells us about the unobservable universe, that fundamental laws like thermodynamics should apply everywhere, that structure formation likely proceeds through the same processes, and that causality separates us from distant regions in ways that make them essentially independent universes. We reflected on the philosophical implications of living in a cosmos so vast we can never fully comprehend it, and we acknowledged the possibility that even if we discovered the truth, we might not be capable of truly understanding it. And we recognized that while we may never directly observe what lies beyond our cosmic horizon, the search for indirect evidence continues, driven by human curiosity and the desire to understand our place in the cosmos. The honest answer: we don't know. After all this exploration, what can we say with confidence about what exists beyond the edge of the observable universe? The honest answer is, we don't know for certain. We have well-motivated theories that make predictions. We have observations that constrain the possibilities. We have mathematical frameworks that extend our understanding beyond what we can directly see. But we don't have definitive proof of what's out there. The most likely scenario, based on current evidence, is that the unobservable universe is simply more universe, more space, more matter, more galaxies, all following the same physical laws we observe here. If the universe is infinite, as a flat geometry suggests, then this, more of the same, continues literally forever in all directions. But we can't rule out more exotic possibilities. There might be other universe bubbles with different properties. There might be higher dimensions we're unaware of. There might be physical phenomena that only manifest on scales larger than our observable universe. There might be aspects of reality that we haven't even imagined yet. This uncertainty might feel unsatisfying. We've come all this way, explored all these ideas, and the answer is, we don't know. But there's something profound in recognizing the limits of our knowledge. It's honest, it's scientifically rigorous, and it leaves room for future discoveries that might surprise us. Science isn't about having all the answers. It's about asking good questions, following evidence wherever it leads, and being willing to say, I don't know, when that's the truth. The questions we're asking about the unobservable universe push at the very limits of what science can address. They force us to think carefully about what we mean by evidence, by observation, by scientific knowledge itself. Maybe someday we'll have better answers. Maybe we'll find indirect evidence that resolves the question. Maybe we'll develop new theoretical frameworks that make testable predictions about the unobservable universe. Maybe future civilizations with more advanced technology and deeper understanding will look back on our current ignorance with the same bemused sympathy we might feel for ancient philosophers trying to understand the heavens with naked eyes. Or maybe this question will always remain at the boundary of what we can know, a permanent reminder of our limitations and the vastness of what lies beyond our reach. Living with mystery, finding meaning in unanswered questions. There's something beautiful about living in a universe that still holds mysteries. Despite all our progress, despite millennia of scientific inquiry, we're still confronted with fundamental questions about existence that we can't fully answer. What exists beyond the observable universe? What happened before the Big Bang, if that question even makes sense? What is consciousness? What is dark matter? What is dark energy? Why do the fundamental constants have the values they do? Why is there something rather than nothing? These questions remain open, and that's okay. In fact, it's more than okay, it's wonderful. The universe doesn't owe us answers that fit comfortably within our intuitions or satisfy our psychological needs. It simply is what it is. And part of the human project is trying to understand it as best we can with the tools we have. Every time we push back the boundaries of ignorance, we find new mysteries waiting beyond. When we figured out that Earth orbits the Sun, we had to ask, what are the stars? When we realized stars are distant suns, we had to ask, are there other planets around them? When we found other planets, we had to ask, do they host life? Each answer leads to new questions, deeper mysteries, further horizons to explore. What exists beyond the edge of the observable universe might be the ultimate horizon question, one we can ask but never fully answer. And yet the asking itself has value. It stretches our minds, challenges our assumptions, and reminds us that reality is vaster and stranger than we often remember in our daily lives. When you look up at the night sky, those distant points of light are galaxies containing billions of stars, many probably with their own planets, perhaps with their own curious civilizations, looking up and wondering the same questions we are. Beyond them lie galaxies we can barely detect. Beyond those lie galaxies at the edge of our cosmic horizon, their light just now reaching us after billions of years of travel. And beyond that, more galaxies we'll never see, more stars that will never illuminate our night sky, more worlds we'll never visit, more stories that will never be told to us. An entire cosmos, possibly infinite, existing beyond the reach of our telescopes and our imagination. Does that make you feel small, insignificant, or does it inspire a sense of wonder at being part of something so incomprehensibly vast? Perhaps both. Perhaps that's the appropriate response to contemplating the infinite or near infinite, a mixture of humility at our cosmic tininess and awe at our ability to even ask these questions, to peer billions of years into the past and probe the limits of existence with mathematics and observation. The gift of perspective. What this question teaches us. Contemplating what exists beyond the observable universe offers us something valuable: perspective. When we're caught up in daily concerns, work stress, relationship conflicts, financial worries, health issues, it's easy to feel like these problems fill the entire universe. But stepping back to consider the cosmic scale reminds us that we're part of something much larger. Our problems are real and important to us, but they're also temporary and local in a universe that extends far beyond anything we can fully comprehend. This perspective doesn't diminish our problems or suggest they don't matter. Rather, it provides context. It reminds us that we're living in a particular moment, in a particular place, in a vast cosmos, and that there are countless other moments and places we'll never experience. It also reminds us how fortunate we are to be alive at a time when we can ask these questions and make progress toward answering them. For most of human history, our ancestors had no idea that galaxies existed beyond the Milky Way. They didn't know about the Big Bang, about cosmic expansion, about dark matter and dark energy. They couldn't look billions of years into the past by observing distant light. We can. We've been given a gift of knowledge that would have seemed like divine revelation to our ancestors, and yet we're still at the beginning of understanding. We know more than our ancestors, but compared to what there is to know, we've barely scratched the surface. The universe is under no obligation to reveal all its secrets to us. We're fortunate to have learned what we have. This perspective can make us more humble, recognizing how little we know in the grand scheme of things. But it can also make us more ambitious, recognizing how much there still is to discover, how many questions remain unanswered, how many frontiers await future explorers. Whether we ever learn what exists beyond the observable universe or not, the question itself enriches us. It reminds us that we're part of a story much larger than our individual lives, a story that extends from the Big Bang to the heat death of the universe, encompassing scales from quantum fluctuations to cosmic superclusters, from nanoseconds after creation to trillions of years in the future. We get to be conscious participants in this story, even if just for a brief moment. We get to wonder, to question, to explore, to learn. That's not nothing. In fact, it might be everything. Closing thoughts. The horizon. Ahead. So what exists beyond the edge of the observable universe? Probably more universe, possibly infinite, filled with galaxies and stars and planets we'll never see. Possibly other universe bubbles, with different properties separated from us by inflating space. Possibly quantum branches where every possible history plays out. Possibly structures and phenomena beyond our current ability to imagine or understand. We don't know for certain, and we might never know for certain. But we can keep looking, keep thinking, keep pushing at the boundaries of knowledge and understanding. The edge of the observable universe isn't really an edge, it's a horizon. And like any horizon, it recedes as we move forward. We can never quite reach it, but we can always see a bit farther, understand a bit more, ask better questions. Future generations will inherit the questions we can't answer, along with new questions we haven't thought to ask yet. They'll have better tools, deeper theories, and perhaps insights we can't foresee. They'll continue the human project of trying to understand the universe and our place in it. In the meantime, we live in this moment, in this place, in this observable universe that's given us so much to explore and wonder about. We can look up at the night sky and know that beyond every visible star lies thousands of other stars we can't quite see. Beyond our galaxy lie billions of other galaxies. Beyond our cosmic horizon lie regions we'll never observe, but that exist nonetheless, following the same physical laws, hosting their own stories, their own wonders. The universe is far larger than what we can see, possibly infinitely so. That's a humbling thought, a dizzying thought, an inspiring thought. And it's a reminder that no matter how much we learn, no matter how far we push back the boundaries of ignorance, there will always be more to discover, more to wonder about, more questions waiting beyond the horizon. The edge of the observable universe isn't the end of anything. It's just the beginning of everything we don't yet know. Thank you for joining me on this journey to the edge of everything and beyond. Keep looking up, keep wondering, and keep asking questions. That's how we honour the vast, mysterious, magnificent universe we're privileged to inhabit. Until next time, clear skies and curious minds to you all.